First thing, sound travels longitudinally. It travels in a straight line. Okay, and we went over that yesterday. Sound travels like this. Okay, it travels like this. You get it? It's a longitudinal wave. It's not a transverse wave. Light is a transverse wave. Sound is longitudinal. You get it? That you can take that to the bank. Easy? Okay, right? Definition. Now, I can though, if I want to, I can mathematically convert this wave into a transverse wave. Right? That's a terrible drawing. Okay? Where these are the compression points, and these are the middle of the rarefactions. Okay? Yes? You get it? So I can convert between longitudinal and transverse. But light is transverse and sound is longitudinal. You get it? Okay, now. That's why I had to say that, because in order for you to understand this, I've got to look at sound as a transverse wave. We know it's not. But I want to look at sound transversely. Okay? So if I have a sound wave, okay, it looks like that. Okay? Yes? That's a sound wave. And I create another sound wave that looks like this. Right? What's the resultant wave going to be? Anybody? It's going to be big, right? It's going to be bigger. It's going to be like this. Right? Yes? Does that make sense? You're going to add them. I can take waves, the same frequency. Right? I can add them together. Down here, I can add them together. Right? I'm going to increase my amplitude. Yes? What is that called when I take two waves, same frequency, same exact wave, and I add them together? What's that called? Well, what's it called? It starts with a C. In your book. Constructive interference. Does that make sense? I do it all the time. I do it all the time. It's constructive interference. Yes? So if you have two waves, I'm terrible at drawing on the board, I get it. Okay, easy? Yes? Yeah. We're making a film. Constructive interference. Okay? Yes. What is it? When two sound waves add together to create a louder or a greater wave with greater amplitude, that's constructive interference. You do the same thing with light. Anything that's a wave. Light and sound. Okay?
Also water.
But with sound, you have much more experience with constructive interference and the next topic with sound. It's all around you. All around you. What happens if I had a wave like this? And I had another wave like this? What? Yeah, they're going to. They're going to add. Yeah, this is. Ready? I'm going to add these two waves together. Right?
You're going
to get nothing.
You're going to get a transversal.
You get nothing. You're going to get nothing.
Beautiful.
Noise canceling headphones. Yeah, so if you have a pair of headphones, a really good pair, it's freaky. It's unbelievable. It is, they're unbelievable, because what happens is this. There are sensors in the earphone that will hear stray noises from the outside. It'll say, nah. It'll say, what's the frequency of those strange noises coming from outside the headphones? What's the frequency? It takes those frequencies and it makes the opposite frequency. It cancels those noises out. So let's say that this is the noise that the earphone is picking up. That's the noise. That's noise. So what the earphone does is it creates a reflective wave that will cancel out that noise. What is this called? Anybody know what this is called? It's a very, if you think this is hard, we have to have a talk. Okay? It's not, it's easy. This is all around you. Does anybody know what the name of this is?
It's called wave deflection, noise cancellation, destructive interference. I was right.
Destructive interference.
Like that.
That's what that's called. It's called destructive interference. Okay? Now,
You destruct the interference.
destructive interference. Now, the next thing is very cool, but you can work, the same effect happens with sound and light. For it to work with light, the distances have to be enormous. Like a star on the other side of the galaxy. I mean, the distances for light, for this to work with light, have to be enormous. For sound, you have experienced this your entire life. Especially you drive, so you have seen this, okay? If I'm standing right here, and I have so this car is stationary. It has a siren on it, okay? It's stationary. These are wave fronts, okay? Right? You hear, this is traveling, room temperature, 340 meters per second, right? And this is a certain frequency. It's a certain pitch, or frequency, or note, whatever you want to call it, right? And you hear it over there. Right? You hear, that's okay, with power failure, but you hear, can you see the board still? Yeah? You hear a certain frequency, do you not? Yes? Now, what happens though if this moves, now this is, let's say this is a kilometer away. Okay, let's just pretend, right? So if this sound source moves fast towards me, what's going to happen to the sound?
Decrease.
What's going to happen to the sound waves if this siren is still sounding, yet this vehicle is moving toward me? What's going to happen to the distance between the wave fronts? Think about it logically.
It's going to grow more.
It's going to be, the wave fronts are going to be closer together or farther apart. They're going to collapse. They're going to be close together, right? So this ambulance or police car or Darcy on the top of a hood, whatever, you're going to, you're not doubling it, you're just going to compress the wavefront, right? So it's a higher, now this is moving, right? So now this is a higher pitch. Right? It's a higher pitch, correct? Yes or no?
Yes, yes.
Okay, good. So what happens when this is traveling very fast? When this, and I'm standing still, when it passes me, what happens to the wave fronts?
It
Do they become farther apart or closer together?
follower.
They become, I thought this was hard, Umar.
It's hard.
But you're getting every answer correct.
I'm guessing.
You should play poker. Okay. You get a lower.
Once they pass you,
What is it?
once they pass you,
Yeah, it went on the other side of it. So in other words, you're right. I should reverse this. So now it's passing you, and now you're hearing the wave fronts are coming like this. Okay, because it's the ambulance is over here now. Right? Yes? Wave front, so you have a lower pitch. And you hear it all the time. You don't know where it is. Right?
It's coming from Mr. Darcy.
Yeah. So when it's going toward you, it's high. When it passes you, it goes lower pitch. What is this phenomenon called? What is this phenomenon called?
it's in the
Named after a guy.
The Doppler effect. Apa sah? Kamu berapa lepas?
The Doppler effect. The Doppler effect is this. When a moving sound source, when a moving sound source is heard by a stationary observer, the frequency of the sound
The frequency of the sound.
by what?
the frequency by a stationary observer,
Wow.
the frequency of the sound is greater
Greater. Yes.
because of the speed of the sound source. One more sentence.
Of the sound.
Of the sound source.
Yes.
The wave fronts literally collapse and become closer together.
Literally collapse.
They collapse and they become closer together. I'm almost done. They become closer together. The wave fronts collapse, become closer together, and it increases the pitch or the frequency of the sound. You get it? Simple stuff. Simple. Yes? So what happens if this is moving away from you?
It increases.
It increases.
Yeah, your wave fronts are increasing. If it passes you, the wave fronts are increasing.
Yep.
Correct?
Yep.
But the pitch decreases.
The pitch is the frequency, same.
So
Okay?
It increases.
Who can shout? Who can scream really loud?
You.
No, I don't want to do it. Who can scream really loud? Abdul, come here. Come here. Extra credit. You need
Mr. Darcy, it's Jaytuna scream loud here.
I want you to go.
Itu mau katakan, dia different. Bisa aku nanti saya Umar lampu.
When I say go, okay? All right, let's see if we can demonstrate the Doppler effect with Abdul. Go! Okay, let's try it again. He's not running. right, wait. You ready? And when I say go, you ready? You ready? Quiet, guys. Listen. Go. Did you see it? You see it? Sorry, thank you. Thank you, Abdul. Did you hear that? Did you hear the reduction in the frequency? Did you hear it? Okay. Come on in, Abdul. Come on in, dude. Thank you. So, as he's running towards the door, I purposely open the door to get the reflected sound in the room. And then as he's passing, the sound is having a hard time getting in here, which is further increasing the distance between the wavefronts. Lowering, that would actually work far better than I thought. That was good, thank you. So do you get it? It's called the Doppler effect. Okay? So I can change up on things. We're not doing the math. That's one reason this is kind of easy. I'm giving you the short version. But let's say that the observer is running towards the sound as the sound is speeding towards the observer. The wavefronts are going to become even closer together. Correct? Yes?
Yep.
And then when the observer who's running passes the wavefront, passes the sound source,
Increases.
it's going to increase the distance between the wavefronts even more. If you're going, look, if you're going 80 kilometers per hour down a road, and the people passing you are going 80 kilometers per hour, your speed relative to the speed of the vehicle that passed you is 160 kilometers per hour. It's double. You get it? So this will work very well. I used to drive an ambulance. Trust me, it works really well. Really well.
You used to drive an ambulance.
Yeah, I was an ambulance driver in one of my former lives. Long story. But this works really well. Now think about it. Think about it.
You are thinking.
Let's say that this is a star traveling towards Earth. Right? You're going to get short wavelengths, aren't you? Yes? And you're going to see them with your naked eye through a telescope. What color is that going to be? Red or blue? Blue. Blue has shorter wavelengths, right? Red has longer wavelengths. It goes like this. Red, orange, yellow, blue, green, indigo, violet. Yeah.
It's rosy.
Yeah, sorry. Sorry. Right? So, this is long wavelengths. This is short wavelengths. So the same thing can be done with light. If the star is coming toward me and I'm observing it on a telescope, I'll see blue, blue-violet, blue-indigo violet, the right side of the spectrum. If it's going away from me, the wavefronts are farther apart, correct? Yes? I'll see red. Have you ever heard in astronomy, blue shift, red shift? You ever hear that? You may now you may notice it. Take out any kind of astronomy, anything. Simple stuff. And you'll see the words red shift, blue shift when it comes to light. This is called the Doppler effect. And it's simple yet complex mathematics. It's not terribly difficult. It's a formula. It's on your equation sheet. But I'm not doing the mathematics with this. Clear? Let's stop it. Okay?